Hello everyone, today we're going to show you how to solve a 1D transient advection-diffusion problem using Nicholson Finite Difference method. Our objectives are shown as below. We're going to present a simple 1D transient advection-diffusion problem. This one is similar to the pure diffusion problem we have seen in the earlier videos. We'll discretize the domain into 5 grid spacings. We'll consider a single time step and solve the problem using Nicholson Finite Difference method. We will vary grid spacings and time steps, and we can obtain more refined solutions. Our problem, the 1D advection-diffusion problem, is shown in the figure here. So we have a porous plate which is 1 centimeter long. We have a fluid flow that's happening inside the porous plate, and the convection velocity in the x direction u equals 0.1 centimeter per second. The property of the fluid, that is thermal diffusivity, alpha equals 0.01 centimeter squared per second. One end of the plate is maintained at 0 degrees Celsius and the other end is maintained at 100 degrees Celsius. The temperatures along the length of the plate varies uniformly, rather linearly, as shown as Tn equals 100 times x over L degrees Celsius. The 1D advection-diffusion equation is given as Ft plus U times Fx equals alpha times Fxx. Here U is the convection velocity and alpha is the diffusion coefficient. F is a dependent variable, and this can be temperature or concentration. For example, if we consider F as temperature, we have Tt plus U times Tx equals alpha times Txx, or represented in another form, dou T over dou T plus U times dou T over dou X plus equals alpha times dou square T over dou X square. Here the uppercase T represents the temperature and is a function of X, the spatial coordinate, and time T. Alpha is the thermal diffusivity of the fluid given in centimeters squared per second. Alpha equals K over rho C, where K is the thermal conductivity of the fluid in watts per centimeter Kelvin, and it is assumed constant. It doesn't vary with the distance. Rho is the density of the fluid in kilograms per centimeter cube. C is the specific heat capacity of the fluid in joules per kilogram Kelvin. We ignore the thermal conductivity and other thermal properties of the porous material itself, as we consider that it doesn't govern this particular problem. So the 1D advection-diffusion equation, we have an exact solution at steady state given as T at x comma infinity, or at large times, equals 100 times exponential of px over L minus 1 over exponential of p minus 1. Here p is the Peclet number and is given as U times L over alpha, and this indicates a ratio of advection to the diffusion. So we'll reproduce the 1D advection equation here as Tt plus U times Tx equals alpha times Txx, which can be rewritten as Tt equals minus U times Tx plus alpha times Txx. We will use the Nicholson method here and to discretize the domain. Here I represent the node location and n represents the time step. Accordingly, we get tin plus 1 minus tin over delta t equals half times minus u times ti plus 1 n plus 1 minus ti minus 1 n plus 1 over 2 times delta x minus u times ti plus 1 n minus ti minus 1 n over 2 times delta x plus half times alpha times ti minus 1 n plus 1 minus 2 times ti n plus 1 plus ti plus 1 n plus 1 over delta x square plus ti minus 1 n minus 2 times ti n plus ti plus 1 n over delta x square. This equation can be rearranged further as shown here. When we consider C equals U times delta T over delta X, where C is the courant or convection number, and D equals alpha times delta T over delta X square, where D is the diffusion number, we then get equation in the final form as shown in equation 4, which is minus C over 2 plus D times Ti minus 1 n plus 1 plus 2 times 1 plus D times Ti n plus 1 plus C over 2 minus D times Ti plus 1 n plus 1 equals C over 2 plus D times Ti minus 1 n plus 2 times 1 minus D Ti n minus C over 2 minus D times Ti plus 1 n. Equation 4 is the finite difference approximation of the original equation when we use Crank-Nicholson method. The finite difference tensile for the CN method is shown here. So Crank-Nicholson method is an implicit method. Here temperatures at present times Tin plus 1 need to be solved for different nodes based on temperatures at previous times Tin as shown in equation 4. But the equations need to be solved simultaneously here, as we have unknown temperatures at neighboring points for the same time step. So this is an example of an implicit method. The advantage being implicit methods are unconditionally stable, so we don't have to worry about the stability criteria in general. But we need to note that the space or time step still need to be smaller for accuracy considerations and not stability considerations in general. The truncation error is of the order of delta t square plus of the order of delta x square. So the accuracy in Crank-Nicholson method is higher than when we use FTCS or BTCS methods. Now let us discretize the 1D domain into NX or say 5 segments, grid spacings equally spaced as shown below from 1 to 6. So note temperatures at node 1 and node 2, node 6 are known, and these are the boundary conditions. To apply equation 4, we need to consider the interior nodes from node 2 to node 5. We have reproduced the equation 4 here, and when we let I equals 2, 3, 4 and 5 for the interior nodes and n equals 0, then we can get a system of equations in the form shown below. Here Tin, T1n and T6n are the boundary conditions for all times, and Ti0 is the initial condition for all interior nodes. We can further rearrange this equation by bringing the boundary condition, which are known for all times, to the right hand side for the first equation and the last equation. And if we let beta equals 2 times 1 plus d and gamma equals 2 times 1 minus d, and let a equals c over 2 plus d and b equals c over 2 minus d, we can rearrange the above set of equations in a matrix form as shown below. Thus, the above form is of the type A times Tn plus 1 equals B times Tn plus 2 times Tbc. Here A and B are matrices and Tbc is the vector for the boundary conditions. Let delta t equals 0.5 seconds. Delta equals L over m equals 1 over 5 equals 0.2 centimeter. We can calculate d, c, beta, gamma, a and b, all these parameters as shown here. The initial conditions are known and is given as tx comma 0 equals 100 times x over L for the various x values for the six different nodes. Also, we know the boundary conditions t0 comma t and tl comma t for all times. Once we substitute the values of c, d, the initial conditions, boundary conditions, etc., and other parameters such as beta, gamma, a and b into the matrix, we can create into the matrix we can get an equation of the form here. So the above equation can be solved using methods such as Thomas algorithm, as the matrix we are dealing with is a tridiagonal matrix, although in this particular case, the upper diagonal becomes 0, but in other cases it may not be. So iterative methods such as Gauss-Seidel, successive over relaxation, etc. can also be used. When we solve the above set of equations using Thomas algorithm, we get the following results when time equals 0.5 seconds. That is, temperature at node 2 T2 equals 15.5556 degrees Celsius, T3 equals 35.0617 degrees Celsius, T4 equals 55.0069 degrees Celsius, and T5 equals 75.0008 degrees Celsius. Likewise, you can find the temperatures at these interior nodes at the next time step by choosing n equals 1 and so on. We will present graphical results using MATLAB for this case. And we can also develop codes in such a way that we can vary the grid spacings and time steps. And we can refine the solutions. We will now go back to MATLAB and run this particular case. So the code for the Crank-Nicholson 1D advection-diffusion equation is written over here. The various parameters are provided here. So for the first case, we'll consider total time t as 1 second and number of time steps as 2. So the first time step is at t equals 0.5 second. And the second time step will be t equals 1 second. So our interest is the first time step, so you can compare the results we obtained using been on the PowerPoint, the results we have at the PowerPoint. So the number of spatial grids nx equals 5. The boundary conditions are given here as Tn1 equals 0 degrees Celsius and Tn2 equals 100 degrees Celsius. We'll run this case and see. Look at the results. So these are the initial temperature profile, and this is the temperature at the first step. Temperatures are given here as 15.55, 56, etc. And we'll look at the values we obtained if we use other methods or if you do it manually. So these results, they match here, 35, 55 and 75. That is what we have here. So we can now run by varying some of these parameters. Let's make t, the total time, as 10 seconds and number of time steps as 20 and the number of spatial grids as 10. And we'll run this program, and we'll compare that to the exact solution that can be obtained analytically as given in an equation in our presentation. So the finite difference method is shown in red and the analytical exact solution at steady state is shown in blue. We can see some gaps. This could be the reason. The reason could be maybe when time equals 10 seconds we are not reaching the steady state, or the error using higher delta x or delta t could result in these gaps. So we'll go back and try to refine our steps. So for the next time step, we'll make total time as, say, 20 seconds and number of time steps as, say, 40, and nx, the number of spatial grids, as, say, 20, and rerun this case. Now these two curves are pretty close, although you can see some gaps. So there is still, we have some more opportunity to refine these grids. So let's make t as 100 and nt as 100 again, and nx as 100, and run this one more time. I think now they are pretty close, the exact solution as well as the solution obtained using Nicholson finite difference method. What we do next is we can look at some temperature profile at different times. So here at the top left hand side we have the temperature at the initial condition when time equals 0 second. At the bottom left hand portion we have the final condition when time equals 100 seconds, and at the right hand side we can see the variation of the temperatures with time. So in this case we have advection-diffusion situation. When compared with pure diffusion, the temperature change can happen quicker in this kind of a setup. We can now go back to our PowerPoint to summarize what we have done so far. In this video, we presented a 1D advection-diffusion problem. We discretized our domain and solved the problem using Crank-Nicholson finite difference method. Note that CN method is an implicit method and is unconditionally stable. And Crank-Nicholson method has a higher accuracy than FTCS and BTCS methods. Here, the error is of the order of delta t squared when compared with FTCS or BTCS methods, where the error is of the order of delta t, although the error is of the order of delta x squared in both cases, whether it is CN or FTCS or BTCS. We varied the grid spacings and time steps and presented the results graphically using MATLAB. In future videos, we can explore more challenging problems. If you have any questions or comments, please post it. Thanks for watching.